Chapter 1. What is API security? API security is the intersection of three disciplines: information security, protecting data; network security, protecting data in transit; and application security, building resilient software. Security is not an absolute state, but is defined by specific goals, primarily the CIA triad. Confidentiality. Data is only accessible to authorized parties. Integrity. Data cannot be modified or destroyed without authorization. Availability. Legitimate users can access the API when needed. A structured approach to security begins with identifying assets, the valuable things that need protection, such as user data, intellectual property, or server hardware. Once assets are known, threat modeling is used to identify potential threats. The STRIDE model provides a useful framework for this. S. Spoofing, illegitimately claiming an identity. T. Tampering, modifying data without authorization. R. Repudiation, falsely denying that an action was performed. I. Information disclosure, exposing sensitive information to unauthorized parties. D. Denial of service, DOS, preventing legitimate users from accessing the service. E. Elevation of privilege, gaining permissions beyond what is authorized. To counter these threats, 5 fundamental security mechanisms are applied as layers of defense. 1. Rate limiting, protects against DOS attacks by limiting the number of requests a client can make. 2. Encryption, protects data confidentiality and integrity. This applies to data in transit over the network using HTTPS and data at rest stored in a database. 3. Authentication, verifies a client's identity, i.e., proving they are who they say they are. This is the foundation upon which other controls like authorization are built. 4. Audit logging, records who did what and when. This ensures accountability and helps in forensic investigations after a breach. 5. Authorization, access control, determines what an authenticated user is permitted to do. This prevents tampering and information disclosure. Chapter 2. Secure API development. Secure APIs are built on a foundation of secure coding practices that prevent common vulnerabilities at the implementation level. Key principles and defenses include preventing injection attacks. This class of vulnerability occurs when an attacker's input is improperly mixed with code and executed by the API. SQL injection, SQLI, is a primary example where malicious input alters a database query. It is prevented by using prepared statements or parameterized queries, which ensure that user input is always treated as data and never as executable code. Input validation. All input from clients must be considered untrusted and validated rigorously. Allow listing is the recommended strategy. This involves defining a strict format for what is considered valid input and rejecting everything else. It is far more secure than block listing, which tries to filter out known bad inputs but can be bypassed by novel attack patterns. Output safety and cross-site scripting, XSS. An API must also ensure its output is safe to prevent vulnerabilities on the client side. Reflected XSS happens when an API includes unsanitized user input in a response. An attacker can craft a request that causes the API to return a malicious script, which is then executed by the victim's browser. Defenses include setting the correct content type header, e.g., application/JSON, to prevent browsers from interpreting the response as an HTML page, and properly encoding any user data included in responses. Chapter 3. Securing the Natter API. This chapter applies the core security mechanisms to a practical example API. It demonstrates how to implement a layered defense. The security controls are implemented in the following order. 1. Rate limiting. implemented as the first line of defense to discard excessive requests from DOS attacks before they can consume server resources. 2. Encryption. HTTPS is enabled to encrypt all data in transit, protecting it from eavesdropping and tampering. 3. Authentication. HTTP basic authentication is used to verify user identity. To do this securely, passwords are never stored in plain text. They are hashed using script, a deliberately slow and memory-intensive algorithm that makes it computationally infeasible for attackers to crack stolen password hashes. 4. Audit logging. A log is created to record all significant API actions, providing a trail for accountability and forensic analysis. 5. Authorization. A simple access control list, ACL, is implemented to define and enforce which authenticated users have permission to perform specific actions on specific resources. Chapter 4. Session Cookie Authentication. This chapter addresses the drawbacks of sending a username and password with every request and introduces traditional token-based authentication using session cookies for browser-based applications. Key concepts include token-based authentication. After logging in once with their credentials, the user is issued a token, a unique random string. This token is sent with all subsequent requests to prove authentication. For web browsers, the standard way to handle this is with session cookies. Session fixation. This is an attack where an attacker tricks a user into authenticating with a session ID that the attacker already knows. The defense is to always generate a completely new session ID immediately after a successful login. Cross-site request forgery, CSRF. This attack involves tricking a logged-in user's browser into sending a forged, malicious request to an API. Since the browser automatically includes the user session cookie, the API processes the request as if it were legitimate. CSRF defenses. Same-site cookies. A modern browser security feature, same-site strict or same-site lax, that restricts when cookies are sent with cross-domain requests. Double submit cookie pattern. The API sets a second anti-CSRF token in a cookie. Client-side JavaScript reads this token and includes its value in a custom HTTP header with every request. The server then verifies that the header value matches the cookie value. An attacker on another site cannot read the cookie to forge the header. Chapter 5. Modern Token-Based Authentication. This chapter covers authentication methods suitable for clients that are not traditional web browsers, such as mobile apps or single-page applications running on different domains. Key concepts include cross-origin resource sharing, CORS, a browser mechanism that allows servers to safely relax the same origin policy, enabling web clients from one domain to make requests to an API on another. It works via a pre-flight options request where the browser asks for permission before sending the actual request. The bearer authentication scheme, the standard for sending non-cookie tokens. The token is placed in the authorization header prefixed with bearer. Client-side storage. Instead of cookies, tokens can be stored in the browser's web storage, local storage. The client-side JavaScript is responsible for retrieving the token and adding it to the authorization header for each API call. This approach is immune to CSRF but more vulnerable to XSS, as an attacker who can execute a script on the page can steal the token from storage. Hardening server-side token storage. When the server stores token data, the database needs protection. Token hashing. The token ID stored in the database should be a cryptographic hash of the actual token sent to the client. This prevents a database breach from immediately exposing usable tokens. Token authentication, HMAC. To prevent an attacker with database write access from forging tokens, a hash-based message authentication code, HMAC, should be used. This involves a secret key known only to the API server, which is used to generate an authentication tag for each token. Chapter 6. self-contained tokens, and JWTs. This chapter introduces JSON Web Tokens, a standard for creating stateless, self-contained tokens that do not require a server-side database lookup on every request. Key concepts include JWT structure. A JWT is a string made of 3 base64 encoded parts separated by dots. 1. Header, metadata, including the signing algorithm, ALG. 2. Payload, claims, a JSON object with the token's data, such as the user ID, sub, and expiration time, EXP. 3. Signature, a cryptographic signature or HMAC that verifies the token's integrity. Security. Integrity, JWS, the signature prevents the token from being tampered with. While the payload is readable by anyone, it cannot be altered without invalidating the signature. Confidentiality, JWE. If the payload contains sensitive information, the entire JWT can be encrypted to create a JSON Web Encryption, JWE, making it unreadable without the decryption key. The revocation problem. The main challenge with stateless tokens is revocation. Since there is no central record to delete, a token remains valid until it expires. To handle stolen tokens, a common solution is to maintain a block list of revoked tokens, which reintroduces a stateful check and negates some of the benefits of using JWTs in the first place. Chapter 7: OAuth 2 and OpenID Connect. This chapter explains OAuth 2, the industry standard framework for delegated authorization, which allows users to grant third-party applications limited access to their data without sharing their passwords. Key concepts include OAuth 2 roles, resource owner, the end user who owns the data, client, the third-party application requesting access, authorization server, AS, the server that authenticates the user and issues access tokens. Resource server, the API that hosts the user's data. Scopes, these are strings that define the extent of the access being granted, e.g., read profile, post messages. The client requests specific scopes and the user approves them. Authorization code grant with PKC. This is the most secure and recommended flow for most applications. The client redirects the user to the AS to get their consent, receives a temporary authorization code, and then securely exchanges that code for an access token. PKC, proof key for code exchange, is a crucial security enhancement that prevents the authorization code from being stolen and used by a malicious app. OpenID Connect, OIDC. This is an authentication layer built on top of OAuth 2. While OAuth 2 is about authorizing access, OIDC is about verifying a user's identity. It introduces the ID token, a JWT, that provides the client with claims about the user and their authentication event. Chapter 8: Identity-Based Access Control. This chapter covers advanced, scalable models for managing permissions based on a user's identity. Key concepts include role-based access control. This model simplifies permission management by assigning permissions to abstract roles. Example, administrator, editor, viewer. Users are then assigned to these roles. This is much more scalable than managing individual permissions for every user. Attribute-based access control. A highly dynamic and powerful authorization model where access decisions are based on policies that evaluate attributes of the subject, resource, action, and environment. For example, a policy might grant access only if the user's clearance level attribute is top secret and the time of day attribute is within business hours. Policy engines and XACML. ABAC is often implemented using a centralized policy engine. The XACML standard provides a reference architecture that separates the policy enforcement point, PEP, which intercepts API calls, from the policy decision point, PDP, which evaluates the policies. Chapter 9: Capability-Based Security and Macaroons. This chapter introduces a different authorization model that is not based on identity, but on the possession of an unforgeable token called a capability. Key concepts include capability-based security. In this model, having the capability is what grants you the right to perform an action. This avoids the confused deputy problem, where a privileged service is tricked into misusing its authority. Capability URIs. In a REST API, a capability can be implemented as a URL containing a long, random, unguessable token. Anyone who has this special link can access the resource, making it ideal for fine-grained sharing. Macaroons. These are an advanced form of capability token that allows for flexible, secure, and decentralized delegation. Caveats. The key feature of macaroons is that anyone holding one can add restrictive conditions or caveats to it. For example, a client can take a long-lived API access macaroon and add a caveat like IP equals 192.168.1.50 to create a new, more restricted macaroon that can only be used from that specific IP address. This can be done without any communication with the server that originally issued the macaron. Chapter 10: Microservice APIs in Kubernetes. This chapter details how to deploy and secure APIs in a modern, containerized Kubernetes environment. Key concepts include Kubernetes architecture, an overview of pods, groups of containers, services, stable network endpoints for pods, and nodes, the machines that run the pods. Container hardening. This involves security best practices such as using minimal distroless base images to reduce the attack surface, running applications as a non-root user, and using a read-only file system. Server-side request forgery, SSRF. A critical vulnerability where an attacker tricks a service into making requests to other internal services. This is prevented by rigorously validating all outgoing URLs initiated by the API. Service mesh. A tool like Istio or Linkerd that creates a dedicated infrastructure layer for managing service-to-service communication. Its main security benefit is providing automatic mutual TLS, MTLS, which encrypts all internal traffic and ensures both services in a communication authenticate each other. Network policies. The built-in Kubernetes firewall, which lets you define rules about which pods can communicate, thereby preventing unauthorized lateral movement by an attacker. Chapter 11: Securing Service-to-Service APIs. This chapter focuses on authenticating and authorizing API calls between automated services where no human user is present. Key concepts include service authentication. Instead of authenticating a user, the API must authenticate the calling service. OAuth 2 Client Credentials Grant, the standard flow for machine-to-machine authentication where a service uses its own client ID and client secret to obtain an access token. Stronger authentication. Rather than using a simple client secret, services should use stronger methods like MTLS, authenticating with a client certificate, or JWT bearer authentication, signing a JWT with a private key. Secrets management. Securely managing credentials like private keys and client secrets is a major challenge. While Kubernetes provides a basic secrets object, dedicated tools like HashiCorp Vault are recommended for production environments as they offer encryption at rest, auditing, and dynamic, short-lived secret generation. Chapter 12: Securing IoT Communications. This chapter adapts standard security protocols for the unique challenges of the Internet of Things, IoT, where devices are often constrained by low power, memory, and processing capabilities. Key concepts include datagram TLS, a version of TLS adapted for unreliable datagram-based protocols like UDP, which are common in IoT to save power and overhead. Pre-shared keys, for highly constrained devices that cannot perform expensive public key operations, a PSK, a symmetric key shared between the device and server beforehand, can be used for authentication instead of a TLS certificate. End-to-end security. In IoT, messages often pass through untrusted gateways. To protect data across these hops, the message payload itself must be encrypted. COES, CBOR Object Signing and Encryption, is a standard designed for this, providing security for binary data payloads. Misuse-resistant authenticated encryption, MRAE. Constrained devices may struggle to generate truly unique nonces for encryption, and reusing a nonce can lead to a complete security failure. MRAE ciphers like SIVAEs are designed to be much safer in case of nonce reuse, preventing catastrophic failure. Chapter 13. Securing IoT APIs. This final chapter addresses the authentication and authorization of the IoT devices themselves. Key concepts include device authentication. APIs must treat devices as first-class actors. Each device should be provisioned with a unique identity and credential during manufacturing. Replay attack prevention. Because transport security may not be end-to-end, the application layer must protect against replay attacks, where an attacker resends a valid captured command. This is done by ensuring freshness using mechanisms like timestamps, nonces, or e-tags in REST APIs. OAuth 2 for IoT, Device Authorization Grant. This is an OAuth 2 flow designed for devices that lack a screen or keyboard. The device displays a short code, and the user goes to a URL on their phone or laptop to enter the code and authorize the request. Offline authorization. Devices must often make security decisions while disconnected from the cloud. This requires the use of self-contained tokens that can be validated offline. A device can verify the cryptographic signature of a token, like a JWT or macaroon, to confirm its validity and the permissions it grants without needing to contact a central server. Macaroons are especially useful here, as they allow permissions to be restricted in an offline context. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe, and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.